Hello. In this video, I would like to introduce counting methods used to compute the number of ways certain things can happen. Probability measures how likely it is for an event to occur. And it is necessary to know how many ways certain things can happen in order to determine an event's probability of occurring. One method for determining the number of ways certain things can happen is by drawing a tree diagram. Suppose you want to know how many different ways you can order ice cream from your favorite shop. Ice cream only comes in three flavors: chocolate, vanilla, and strawberry. The ice cream can be put onto a cone, into a cup, or made into a milkshake. Each could be ordered as a small, medium, or large. You could try to determine the number of combinations by keeping count. For example, a small chocolate cone is one example. A medium chocolate cone is another example. And a large chocolate cone is a third. Tracking the options this way is a bit tedious and presents the possibility of easily miscounting. A tree diagram can be used to map out all of the options with branches stemming from each choice. I'll start with the first three branches, one for each of the three flavors of ice cream. On each branch, I'll draw three more, one for each type of ice cream. Finally, three more branches, one for each size, finishes the tree. You will notice that by following each possible branch or pathway, we have created every possible way that the ice cream can be ordered from this shop. Please pause the video now and count the number of branches on the right side of the tree diagram. You should have noticed that there are 27 branches, which means there are 27 ways to order ice cream from your favorite shop. You may feel that this method is not only tedious and time-consuming, but it also requires the use of much of your notebook for just one problem. You may have also noticed that there is a shortcut for counting these possible outcomes. The fundamental counting principle dictates the number of options for each independent component of a multiple component event should be multiplied together to count the total number of options. If the first component can occur X number of ways, and the second component can occur Y different ways, and a third component can occur Z different ways, then the total number of different outcomes is X times Y times Z. This method holds true for any number of components. For our ice cream example, we had three options for the first event, flavor, three options for the second event, type, and three options for the third event, size. 3 times 3 times 3 gives us 27. The same number of outcomes we determined from the tree diagram. In the case of license plates for vehicles, many states have decided to use 3 letters and 4 numbers to uniquely identify vehicles registered in the state. Take a moment to determine how many unique license plates can be made using this combination of letters and numbers. Pause the video now and resume playback in a moment to check your work. Each letter has 26 options, A through Z, and each number has 10 options, 0 through 9. So there are 175,760,000 unique options for license plates. Sometimes, when counting the possible outcomes for a multiple component event, one outcome affects the next. For example, when determining the number of ways 8 people can finish a race, once a person takes first place, they are not eligible to finish in any other position. So, while there are 8 different possible outcomes for first place, there are only 7 possible outcomes for second place, and so on. This is an example of the fundamental counting principle. Factorial notation is used to abbreviate the multiplication of whole numbers that descend like this. Some calculators have a special key to perform this task. If we were only interested in the number of ways the top 3 could finish, we would only multiply the first 3 numbers of the factorial, because we're not interested in the outcomes of fourth place, and so on. Special notation is used to identify this permutation, NPR, where N represents the number of items in the set, and R represents the number of items that are needed per grouping. And NPR is computed this way: N factorial divided by N minus R factorial. You can see that the result is the same as before when computed using the fundamental counting principle. We say that order matters here because the number of outcomes counted include all different ways that the top 3 can finish. For example, racers A, B, and C that finish in that order is counted differently from C, B, then A, or A, C, B, etc. When order does not matter, say in the hand of poker using a deck of cards, we use the combinations formula. A small change to the denominator eliminates the individual outcomes using the same objects. In a 5-card hand of poker using a 52-card deck, for example, it does not matter if you are dealt a ace first, then king, or a king, then an ace. Both mean the same thing towards your final hand. When computing the results of permutations and combinations, it is helpful to have a scientific calculator that has a factorial key. If you're lucky, you might even find a key that completes all steps of the calculations at once. Take a few minutes to practice the final calculations on your own. Pause the video now and resume playback in a moment to check your work. Good luck.